Today is the recomposition and specifically concepts relating to performance and state issues during the recomposition. And this is hopefully building a little bit on last month's presentation. And I think those internals was mentioned last time. A lot of this information comes from there, but along with several other sources. And what I aim to do here is not make a super deep dive. I don't really care about how the Compose compiler is coded or the algorithms that are used on the slot tables, et cetera, et cetera. Though some of that information is available in that book. Here, I'm going to try to look more at just some concepts that might be useful in the course of, potentially debugging issues with Compose or preventing those issues in the first place. So first, I want to look at just a couple of tools that are available for analyzing or debugging Compose. And the first of those is recomposition counts. As of Android Studio Dolphin, which I think just went stable, Layout Inspector has an option to show real-time recomposition counts throughout the composable tree. And in this case, if you can see my cursor there, we just need to make sure that we actually turn on recomposition counts under the little eyeball here, and then also turn on your live updates there. That will show you on the left column the number of times a specific composable has been recomposed and the number of times it has been skipped during recomposition, and we'll address that a little bit more later. Then, as of Android Studio Electric Eel, the Layout Inspector will highlight active recompositions in red, and then that color will just kind of fade away over time back to white. So you can see ongoing recompositions, and you can also kind of tell which ones were most recent just from the shade of red you get there. So that's the first tool to look at. The next is Compose Metrics. This is more geared towards, I guess, broad or preemptive analysis of your composables and any issues you might have with them. You can generate the Compose metrics from a release build by adding this block of code to build.gradle in the root project, and then running the command at the bottom in your terminal. And what you will get out of that is a Compose metrics folder inside of the build folder, and that will contain 4 different files. The first one, the classes.txt, will show a rundown of non-composable classes that are relevant to or used by potentially your composables. And it's going to show for each of those classes the compile time and runtime stability of the class or of any fields within that class. And we'll address that a little bit more later. Next, you get the composables CSV file, which shows all of the composables in that module, along with several columns of information about those composables. And the 2 columns that will be of interest to us during this presentation are skippable and restartable. Next, you have the same information just presented in a text file showing each composable. Is it restartable? Is it skippable? And are its parameters stable or unstable? And then finally, you'll get module.json, which contains module-wide statistics on the composables in your app. We already mentioned, skippable composables, restartable, a number of other things there that we don't need to go through item by item. So those are the two tools I wanted to mention, the recomposition counts and compose metrics. With those out of the way, I want to look at some of the key words that were shown in those tools. And specifically, I want to look at restartable, skippable, and stable, what those words mean, and then we'll drill down into that a little bit, and then maybe towards the end we'll zoom back out to the bigger picture of the recomposition cycle and how that fits in. But we'll start with restartable scope. A composable may or may not have restartable scope, or may not be a restartable scope, I guess I should say. The composables have restartable scope by default, unless one of the three conditions shown in this slide are met. If it is an inline function, it does not have restartable scope. If it is explicitly annotated as non-restartable composable, then of course it does not have restartable scope. And if it returns something other than unit, it does not have restartable scope. And something to keep in mind as we go along, and I'll address this more, several common composables are inline functions and thus are not restartable scopes. Those include most notably column, row, and box. There might be more, but those are the obvious ones. Okay, so then still, what does restartable scope mean? A restartable scope is a sort of way station or perhaps a retaining wall during the recomposition process. And then it also relates to the grouping of composables in the composable tree, whether something is defined as a restartable group, movable group, etc. Not worried about that part too much right now, just worried about the restartable scope. So when a change to the state of some data triggers recomposition, the runtime, the compose runtime, will search up the tree, up the hierarchy for the nearest restartable scope where it can begin that recomposition process. If a composable does not have restartable scope, then the runtime will check its parent and that parent and so on until it finds a restartable composable. And from there, it will run the recomposition process for it and for all of its children, or all of its descendants, I guess. So this is maybe the first important point here, that failing to account for restartable scopes may result in a recomposition propagating to far more composables than you expect. And that may have unintended consequences both for performance and state. Looking at this example that I'm already showing right here, I've already mentioned that column, row, and box are not restartable. However, box with constraints is restartable, and a lazy list item is restartable. So when I run this code, there's nothing really to display on the UI except for that innermost text composable. That depends on the variable selected, which is changed after 5 seconds by a launched effect. So when selected is changed, that invalidates the parameter passed to the text composable and triggers the recomposition process. The compose runtime seeks out. Oh, and by the way, if anybody wants me to stop, or the way I have my screen set up right now, I'm not seeing the chat. So if you want me to stop at any point or go back, just interrupt me, and I will do so. That's not going to bother me. But so the selected is changed after 5 seconds. That invalidates the parameter passed to text. And the compose runtime will seek out the nearest ancestor with restartable scope and begin recomposition there. In this case, since the lazy list item is restartable, we don't have to go up the tree at all. We just stick with item, and that's the only one that gets recomposed. And we can see that in the printout from the logs here. So if we can follow my cursor, from greeting down here to the first item, that's just the initial composition. Greeting being the outermost composable that contains all of this other stuff. So greeting gets composed, column, box with constraints, box, row, lazy column, and item. After 5 seconds, only the item gets recomposed. Since the invalidated parameter is isolated to this text composable and item has restartable scope, that's the only thing that gets recomposed. And I also want to note, just in case it's relevant to anyone, that it doesn't matter where that variable or launched effect are initialized or run. What matters is where that data is passed as a parameter. So whether I declare this launched effect or the variable selected inside the item or outside of it, doesn't matter. It's still the same result because the selected variable is used inside text. Now, in the next slide, I am moving that text composable out of the item to be a direct child of row. And in this case, what we're going to see is that since row does not have restartable scope and box does not have restartable scope, then we will recompose everything beginning with box with constraints. That's the nearest ancestor with restartable scope. So that means box with constraints and all of its children will get recomposed or at least checked by the recomposition process. And, we'll look at that a little more later. So in the logging, we can see that very thing here. Again, we have our initial compositions from greeting down to this item. But this time, when that piece of data changes, the recomposition starts with box with constraints and then progresses to box and then to row. Now, I kind of alluded to a slight distinction in idea between the recomposition process and being recomposed. And what I mean is that the compose runtime will attempt to optimize the recomposition by skipping composables wherever possible. If it doesn't need to actually re-execute that composable and rematerialize it and all of that stuff, it will skip it if possible. And there's actually an implied example of that right here. Yeah, so we'll look at that. Oh, no, I didn't show that here. Okay, so let me go back here. Sorry, I backed up a little too much. Yeah. In this case, you'll notice that when the recomposition happens, we do box with constraints, box and row, but we actually do not do the lazy column or the item here. And that is because this item is actually skipped. So the compose runtime does an optimization and skips recomposing item. So why does it do that? How does it do that? So that takes us to skippability. A composable can be skipped during the recomposition process, provided that it meets 3 requirements. 1, it has to be a restartable scope. A composable cannot be skipped if it does not have restartable scope. So, for example, a box, row, or column can never be skipped, which means in turn that all of their children will be checked during the recomposition process as well. Um, but that doesn't mean that their children cannot be skipped. So any particular child of a row could be skipped, but the entire row cannot be skipped. So one, it has to be a restartable scope. Two, and this one is kind of self-explanatory, I think, it must not depend on any of the changed data that triggered the recomposition. Um, so in this case, the text composable depends on selected. That's never getting skipped, obviously, in this case, because it actually depends on the data that changed. And three, is that the composable must not depend on any other data or any other parameters that are inferred to be unstable. So what does that mean? Unstable. How is a parameter inferred to be unstable? Okay, well, first of all, there are two levels of stability in Compose: immutable and stable. Although I believe, for all intents and purposes right now, those are treated in the same way. Maybe they will be separated in the future. But there are at least two different annotations that can be used: immutable and stable. Immutable would mean, of course, that the data, once created, will not be changed. And that can be effectively declared in two ways. One, with the @immutable annotation, as shown in the data class down here, or that can be done with using um, only immutable collections items. And we'll look at that more later, the immutable collection item library. But then we get to stable. A stable parameter is going to be one that is either not mutable, irrespective of whether it contains the @immutable annotation. A stable parameter is one that is not mutable, or one that can be mutable, but is expected to notify the runtime of any changes to itself by way of being backed by mutable state of or an equivalent. And that is, after all, how the recompositions get triggered by those classes like mutable state of, which implement, snapshot mutable state. We'll look at that later. But in other words, a stable parameter is one that the runtime can be certain of the state of at all times. So looking at some more specific examples here and how Compose will decide on the stability of parameters. The compiler will first attempt to infer the stability of any parameters. If it is not able to, it will pass the job off to the runtime. The case where that might happen would be like if you have generics or something in there. But whether the compiler or the runtime is doing it, primitive and string parameters, along with a few other types, will always be inferred to be stable. Collections objects will always be inferred to be unstable. Right? So a string parameter is always stable. A list set map is always unstable. And one other notable notable object or class that would always be considered unstable is a view model. So collections objects and view models are always considered unstable. And one note worth mentioning is that that may not always have been the case, and it may not be the case in the future. There's a playlist on YouTube from Leland Richardson, who is one of the engineers on Compose, made during the alpha phase of development, that stated in one of those videos that they intended to actually um, trace back to the instantiation of a list to determine whether it was list of or immutable list of or whatever. But that has not happened yet, at least. So any list, set, or map passed as a parameter is just unstable. Additionally, object stability propagates to parents. In the case of the data class SumData, since item one is a collections object and collections objects are inferred to be unstable, the entire data class SumData will be inferred to be unstable as well. And also, if you maybe this goes without saying, but if you declare the fields of a custom object or class as var rather than val, then that will also cause it to be inferred as unstable. If a composable depends on a piece of data that is considered, or depends on a parameter that is considered to be unstable, that means it cannot be skipped during recomposition. So in this little example here, if anything triggers the recomposition of the composable greeting, that first text composable will always be recomposed regardless of anything else because its parameter is unstable. If, on the other hand, all of the parameters are stable, it might be skipped as an optimization. And this is a little bit more of an involved example that will highlight some more specific cases and examples of this. So we have data point one that is a list backed by mutable state of. We have data point four that is a string. And these in turn are getting passed down to greeting, and then getting passed in turn to custom text and to text respectively. And then there's a launched effect in there that's going to attempt to alter those. And if we run the compose metrics on this, we will see that, in fact, data point one is considered to be unstable. Data point four is considered to be stable. And it's worth noting here that even though data point four is declared as a var, and even though we are attempting to change data point four inside of the launched effect, it is still considered to be stable as a parameter to greeting. So next slide, yeah, that's just the same thing. Okay. So I want to show you what happens here when we actually run this. So from the recomposition counts, we see that custom text gets recomposed every time. Text gets skipped every time. And this perhaps is unexpected since we're trying to change both variables. But of course, recall that data point four is just a string, and a string will always be inferred to be stable. And two, I alluded to this earlier, and I'll address it more later. Since data point four is not backed by mutable state of or something equivalent, the compose runtime doesn't actually know that it's changing. So we are recomposing greeting, 100 times, because inside of that launched effect, we're changing data point one that is backed by mutable state of, that's triggering the recomposition. When the recomposition runs, it is, of course, recomposing custom text because that depends on data point one, but it is not recomposing, or rather, it is skipping the text composable because data point 4 is inferred to be stable, and it doesn't know any better whether or not data point 4 has changed because there's no mutable state there. In the next slide, I'll make a slight variation here, which is just that the custom text down here at the bottom now only depends or only takes as a parameter a single string, just the first element in what this list is. So that's the only change. Instead of custom text taking the entire list, it just takes the first element, which is a string. If we run this again, we will see that actually everything is getting skipped. Now, why exactly is that happening? Or what exactly is happening here? Okay, so data point 1 is still backed by mutable state of, and data point 1 is still being changed 100 times in this launched effect. And that change to data point 1 is actually notifying the compose runtime and is actually triggering the recomposition process. And if I were to add a logging statement in here inside of greeting, we would see that greeting is actually getting recomposed here, or at least the recomposition process is running. But in this case, we are able to skip both children. All right, why are we able to skip both children? Well, we know why we're able to skip the text composable. We're able to skip custom text now because its parameter is now a stable string, and that string, being the first element of the list, is never changing because I'm only adding to the end of the list here. So both of these get skipped. And since both get skipped, it doesn't increment the recomposition count here. Just be aware that the recomposition process is running 100 times, and there is some overhead associated with that. But it's skipping everything, so it's not incrementing. Okay, and then in the next slide here, I will make one more variation right here in the launched effect. So now instead of adding to the end of the list, I'm adding to the beginning of the list. This is still the same. I'm taking the first element, which is a string, as a parameter. The list is being changed 100 times. The compose runtime is being notified of that 100 times because it's backed by mutable state of. In this case, this first string is actually changing every time. The runtime knows it, and so that custom text once again gets recomposed every time. Text still gets skipped. And again, stop me at any point if there are questions or discussions or anything else. If not, I will continue along. Okay, one more example here. Just to verify that unstable fields or parameters do propagate up. In this case, rather than having a list of strings, we have a list of some data. The field item 1 in some data is inferred to be unstable because it's a list. As a consequence, the entire class some data would be considered unstable if passed as a parameter. And in this case here, we are passing an instance of some data as a parameter. All right, we're only taking the first element of this list, but in this case, not only is the list unstable, but some data is unstable. So that first element is still some data, and that is still unstable. And here, I've changed this up at the top. So now data point 4 is backed by mutable state of, and I'm only changing this. I'm only changing that string that gets passed to this other text composable. So runtime, I mean, compose is triggering recompositions based just on this. However, both composables get recomposed every time because that sum data class is considered to be unstable. So before we move on, what are some quick fixes or suggestions for some of this stuff? Well, wherever possible, you should try to pass specific stable fields through composable parameters rather than entire objects. And that also includes view models. View models being an unstable type, it's probably not the best idea to pass a view model all the way down through your tree. Instead, pick out, the fields or the bits of data that you need and pass those individually. As mentioned earlier, if you're on recent versions of Kotlin and the Compose compiler, I think the former requires 1.6 point something, and the latter maybe requires 1.3. The immutable collection library is available as an alternative to the regular collections library if you know that you are not going to be changing the elements of a list, set, map, whatever. And then as a last resort, you can yourself explicitly add the @stable or @immutable annotations to any class and insist that the Compose compiler or runtime treat it as such. However, there are no compile time or runtime checks against the veracity of the usage of those annotations. So you're on the hook for upholding that contract and or for any weird behavior that might result if you don't. Okay. Moving on then. The next section, slot tables, snapshots, and synthetic parameters. So in the course of those last two sections, maybe, at least for me when I was doing this, there were a few questions that still came up. Why does a composable evaluate to skippable, even though it has stable parameters that have changed? Why are changes only applied when backed by mutable state of or something equivalent? And why is an unstable parameter not backed by mutable state of still forcing recomposition, even if the runtime isn't bothering to actually update its manifested values in the UI when it changes? Some of that is ultimately down to choices made by the engineering team at Google, but some of it can be addressed, at least to a degree, by looking at the topics in that header there. So the slot table. When an activity called set content, Compose begins the process of creating all of the intermediary objects that it needs: the applier, the recomposer, one or more composers. We don't need to look at that right now, but you're free to investigate on your own. And then it will make a first pass through the composable tree and fill in two tables, a groups table and a slots table. The groups table just contains metadata, indexing, and keys as references to composables and composable groups. In the slot table, which is where all of the other information that is actually required to maintain and update the composables and or their place in the tree lives. I'm not going to spend a lot of time here on those data structures. I'm by no means, I haven't looked through in detail exactly how they're managing all of that. We just need to know, I think, here that ultimately the relevant data for the composables is contained in that slot table, which is, I think, just Google's own terminology. It's a gap buffer, basically. The next topic, though, is synthetic parameters. And this is a little more interesting. When Compose processes your composables, it adds synthetic parameters that perform a variety of functions involved in the composition and recomposition process. This bit of code shown here on the screen is omitting quite a bit of stuff here. I really should put like ellipses, at the beginning and end of that. But in any case, the most interesting synthetic parameters here are the composer and the changed parameters. Composer is what does most of the work in here during the recomposition process. It will start a read or update on a composable group. It will end the read of that composable group. And also in there somewhere, it's going to um, start a snapshot and apply a snapshot, which we will talk about later. But for this slide, we're looking at the parameter changed. Changed is a bit mask that encodes 2 bits for each parameter in your composable function. And these 2 bits may be determined again at either compile time or at runtime. 0 means uncertain, 1 means same, 2 means different, and 3 means static. And roughly speaking, uncertain would refer to an unstable parameter. Same would refer to a stable parameter without any observed changes. And different would be any parameter with observed changes via mutable state. And then there are going to be some bitwise operations. At the end of those, same and static will always evaluate to skippable unless a recomposition is being forced either programmatically or for some other internal reason. But uncertain and different never will. So this is kind of the point in the cycle at which we can zero in and say this is exactly why unstable parameters always cause recomposition. They will always evaluate to uncertain, and that will always evaluate to not skippable. Now, I mean, as to why they chose to do it that way, I don't know. Maybe somebody else knows. Um, I have not gotten that deep into it. The next thing that I mentioned were the snapshots. All right, so within that, if we go back to this last slide here. Oh, where is it? Yeah. So if I were to show the full code of everything that gets added into this composable function here by the compiler, somewhere in here, it's adding a bit of code that looks in some vague approximation like this. It's going to start a mutable snapshot and apply an observer to it. Roughly equivalent to whatever the current group is, the restartable group, restartable scope, whatever. So that snapshot is going to observe changes to mutable state objects. And then when the recomposition of that composable is finished, the last thing that's going to happen is it's going to call snapshot.apply. And this is a form of what do they call it? Multi-version concurrency control or something. So basically, each composable group has its own mutable snapshot. And once that composable group is finished with its work, then that snapshot is applied. So all of these, and I should say, let me back up and say that the snapshots themselves form a tree structure. There is one global snapshot root and any number of mutable snapshots beneath it, again, corresponding more or less to different composable groups. So each composable group holds its own snapshot, until it finishes whatever work it needs to do during a cycle, and then it applies its snapshot. And as these snapshots are applied, they are merged and resolved with other snapshots further up the tree. And as recompositions finish, we go further and further up the tree towards that global snapshot root. And once the entire process is complete, then that global snapshot is advanced, and any changes contained therein are compared to the data in the slot table. And then we trigger a new round of invalidations and recompositions. And this circles back around to one of those questions of why it has to be like mutable state of or something like that. So we see in this previous example, if I go back here, we have this observer here that is observing whatever changes to state take place during this process. But only classes implementing this snapshot mutable state interface will write to those snapshot observers. And thus, only those classes will get applied to the recompositions. Any other data is effectively invisible to Compose after its initial placement in the slot table. It's kind of a set it and forget it if it's not backed by something implementing this snapshot mutable state. The most common classes or transformations that provide this are mutable state of, but then there's also mutable state list, mutable state map, derived state of. And then if you're using flows or live data, you can use collect as state or observe as state to transform those into a snapshot mutable state. So that kind of concludes the section in which I wanted to dig into some of those concepts. If there are no questions or comments at the moment, then I'm going to kind of back out of that a little bit and just look at some more specific cases um, where there might be some gotchas in Compose that might be understood better once we know those concepts. Anything I need to stop for any reason, I'll take silence as a no. Okay.
When is, when is
Sorry.
when is the best moment to use a snapshot?
That snapshot, that's all done for you by the Compose runtime. That's not something that you need to worry about. But I'm giving some discussion here of how it works because what you do need to know is that you need to have, if I can back up to one of these, find some example here. If I go back to this example, right, I want a piece of data, any data that I'm using um, that might change uh, in a composable to use this mutable state of or mutable state list or collective state or something like that. I don't need to worry about the snapshots, but I need to use this in order to have those snapshots record changes to my data, if that answers the question.
Yes, makes sense.
Oh, okay. Mhm. Okay, so the next thing here, yeah, the next thing here in terms of additional gotchas are unstable lambdas. So remember that when compiled, the lambda is going to become an anonymous class, and any necessary or implied parameters are going to be added, and those parameters can be unstable. In the case of Compose, the most common scenario, at least in terms of work that I've done. The most common scenario for this is the invocation of view model methods within those lambdas in response to user actions. And if you recall that I said on one of the early slides that Compose considers a view model to be an unstable parameter, then we can see how this could become a problem, especially if you're using lazy lists or other large sets of content where that lambda ultimately is passed all the way through to like a click method for each composable or something, just as in this example here. Now, I didn't write this one. This one is taken from the Stitch Fix developers blog, just so I'm not stealing it. But everything here kind of looks kosher, right? I mean, we're using collective state there. So the names are being passed in a stable and stateful way. And although you can't see the actual view model methods here, you can trust me when I say that, when I click add name, I'm always just adding a name to the bottom of the list. So we shouldn't be repositioning any items in the list and triggering a recomposition that way. I'll also give more on that later. But in spite of using collective state here to pass the names through, and in spite of only ever adding to the end of the list, every composition tracking name composable here gets recomposed every single time a name is added until that composable exits a screen or exits the composition or hits some other optimization. But we can see here in the composition counts that as I continue adding these composables, all of the previous ones are getting recomposed again. And that's because when this lambda is compiled, it's adding a parameter for the view model, which is considered unstable. And that in turn is getting passed all the way through down to each of these composables. And that means every time something changes, all of these have to change, or all of these have to be recomposed. In this specific case, the solutions would be either to replace the inline lambdas with method references, which will not be unstable, or to use remembered lambdas. I think the first option is the most common and the preferred one. But either of these options, replacing the inline lambda with a method reference or a remembered lambda, now allow us to skip, as we can see here, all of these composition, tracking name, whatever, get skipped each time a new one is added. So that's the specific case of if you have the issue of the view model being passed through. In a general case, it's the same sort of fix that has been mentioned before, that if you're using lambdas for your clicks or whatever else you need it for, try to only use stable types within that lambda so it doesn't create parameters for you that have unstable types. The next gotcha is the data classes from other modules. So a class can only be inferred as stable if it resides in a module built with Compose. In the case of third-party libraries or other modules for which this is either not possible or not worth it, then those classes or objects will be inferred as unstable, even if they actually meet all of the other requirements for stability. So in these cases, same kind of ideas as before. If possible, pass specific stable, pull specific stable fields out of that data class and pass that through the composable rather than the full class, or just map that external class to one that is internal to the module that you are using, that is built with Compose. Next item is don't forget to remember. And this is a situation that came up in an app I was looking at recently here. And I wonder if, just quickly, and like off the top of your head, does anybody see anything that might go wrong here? I will also take silence as a no. All right. So the issue here is that no matter how many times I click on that button, the UI is always going to show stale rather than fresh. Right now, item is backed by mutable state of. So the compose runtime knows that the on-click method is changing it. And it also knows that it is being passed as a parameter, or at least an element, a field of it is being passed as a parameter to text. So why does the UI never update to fresh? Well, in this case, the reason is that when the recomposition process reruns the composable that contains this block of code, it is also rerunning the value assignment of item. And it is setting it back to, even though the button click changed it to fresh item, when the recomposition runs, it's running the value assignment again and setting it right back to stale item. And then that is what gets passed down to the composable. So in this case, we need to remember one more thing, which is remember, and adding that remember block, putting that within a remember block, tells the compose runtime to remember any changes that we make to this value across recompositions. Now, if I leave the screen or this leaves the composition entirely, if I tab over to another screen and come back, depending on the structure of my app, then this might still be reset. But by using remember there, it remembers updates to that value across recompositions without resetting it. So now, just by adding that, after the button click, the UI will now correctly show the word fresh here. And then the last gotcha, and I'm kind of hoping somebody gets this reference here. Trust me on the sunscreen. If not, that's fine. I'm a little disappointed, but that's fine.
I gotcha.
Okay. So this is kind of the easiest win, I think, in terms of these composable stuff, which is that for any lazy lists or any other large group of composables that might be subject to reordering or deletion, insertion, etc., if possible, take advantage of the keys. Take advantage of providing your own key to that composable. Composables in that slot table are positionally memoized, and the keys used to identify them are by default a hash based on that position. So if the position in the tree changes, that is also something that will invalidate that that composable and cause recomposition. In the case that you have a large list of items and an item is inserted or deleted from the front of the list, then every item after that has a new position. And if you have not provided a key to it, and if the default key is based on that position, then all of those items are getting recomposed, regardless of any of their parameters or anything else, right? Because that positional key has changed, all of those are getting recomposed, and depending on the complexity, the size, the number of those items, you could easily get into hundreds or thousands of unnecessary recomposition, hundreds or thousands. I mean, I don't know, maybe hundreds of thousands, but probably hundreds or thousands of unnecessary recompositions in a pretty short time. So providing your own key just allows a different way of that uh, of those tables referencing the composables so that they don't have to be invalidated because their position changed and that changed their keys. And just to show the example here, this is run on a lazy list initially without keys. Each time I was adding something to the top of the list. So it looks like here, each one of these got recomposed 5 times, roughly corresponding to however long they were actually on screen or run into some other optimization. But if I provide keys, then none of those uh, have to be recomposed, whether I'm adding to the beginning of the list, adding to the end of the list, removing something, etc. Only that specific item needs to get composed or recomposed, not everything. So that's it. That's what I have. Unless anybody wants me to go back, look at something else, I'll shut this down for whatever discussion or anything you guys tend to have next. All
Are
right.
there any lint checks that catch some of these things at development time?
I believe I've seen lint checks that will suggest like the method references thing as an alternative to like the lambdas. But like something like the keys, no, there's no lint check for that that I'm aware of. Nor are there any lint checks relating to stable, unstable, mutable state, any of that stuff. At least right now. So the restartable scope, the inferred stability, um, and the consequences of those things, you're kind of on the hook for being aware of that. Um, um, and applying that as you will, as far as I know or can tell.
Awesome, thank you.
All right, cool. I'll stop sharing then, and move on to I don't know whatever else you have here, Greg, but that's it for me.
Yeah, thanks, Jonathan. Does anybody have any other questions for Jonathan? Or if not, then we can go ahead and head out. Oh, Sierra mentions that there's open source lint rules in the chat there.